Hello everyone, we are going to start the discussions on the Hartnell Governor. In the last sessions, we have completed the Watt Governor and Porter Governor as well as the Powell Governor. But this is somehow different from the other governor because if I'm talking about the Hartnell Governor, this is basically a spring controlled governor. When you say spring, there is a force, spring force F is equal to kx, so which is directly proportional to the displacement. Force is directly proportional to the displacement, and when you draw the diagram between the force and the displacement, you will get the straight line curve. So basically, when you see the graph of spring control governor, you will get straight line. Okay. However, there are another cases for a stable governor, unstable, and the isochronous. But the basic understanding is that spring control governor having the graph which is a straight line. Okay, so let me draw the diagram of Hartnell governor, so we will see each and every term of the Hartnell governor. Since we know that the governor is mirror image, they are symmetrical about the spindle axis. Okay, so this is your all arm. Okay, we will see later what it is called as. But first we need to draw the diagram. And what is this? What I am going to draw? You all know very well this is basically the sleeve. Okay, you can see in the diagram there are two arms. Okay, the one is vertical arm and the second is horizontal arm. Okay, and this is your spindle. This is your spindle. Okay, this is your spindle. And the one most important thing about the spring control governor, that there is a spring. There is a spring. We all know that there must be a spring, but the spring must be in compression. That means we can say it should always in compression. Okay, where is the spring? You can see here the springs are like that. This is your spring, and sometimes it is called as the helical spring. Okay, like that. Similar types of arm would be in opposite side. Okay, symmetrical to previous one. Okay, it would be symmetrical to the spindle axis like that. Okay, and what it is called? See, this vertical arm is known as, sometimes examiners will not give you horizontal or the vertical, they will give you another name. So if examiners gives you ball arm, so it is vertical arm. Ball arm means the arms where ball is attached. This is ball arm, and it is also known as vertical arm. This is also known as vertical arm. Okay, similar, this is also ball arm and the vertical arm, and this is another arm which is known as horizontal arm or sleeve arm because it is connected to the sleeve. So we will call it as a sleeve arm. Sleeve arm. Okay, and the length of ball arm is considered as A, this is B. Okay, is that clear? So what I'm going to say, this is the helical spring. This is helical spring. And again, I'm repeating that it is always in compression. What is the role when it is always in compression? We will see. Okay, but here you must remember that it should always in compression, because when the spring is always in compression, always the spring force will be in the downward direction. There will not be any spring forces in the upward direction, whether sleeve move upward or downward. Always spring force work in the downward direction. That means the spring is in compression. Okay, that is the meaning. So when I say that the spring is in compression, that means the spring force always in the downward direction. It never will be in the upward direction whether sleeve moves upward or downward. Okay, it should be in compression. It should be in compression, always in compression. Okay, any doubt? So what will happen? Sleeve can move upward and downward, we all know that. So as sleeve move upward, the vertical arm will having different angle from the vertical. Okay, that means now it is having 90-degree angle. Okay, you can see on the plane of paper it is showing 90-degree angle, but when the sleeve move upward, so the new position would be like that. Let me show the another position when the sleeve move upward. So first I'm going to show you the lower position, then we will see upper position. Lower position. There is a lower position. Okay, lower position of the sleeve. You can say lower position of the sleeve. So when the sleeve is at a lower position, the position would be like that. It would be like that. Is that clear? Is that clear or not? This is your ball arm or a vertical arm, and this is your sleeve arm. Okay, so there will be a, see, there is a sleeve which is having the mass capital M. Okay, there is no friction forces, only spring force is there, and we all know that the spring is always in compression, so the spring force will be in the downward direction always. Okay, and since this governor is identical about the spindle axis, so we will consider only one part, one sided. So there will be mg by 2, and another side there will be a sleeve mass which is mg by 2. Okay, so we are going to consider only one sided portion for the calculation. So there will be a mg plus fs 1 by 2. Okay, are you getting my point? Why I am considering here plus sign? Because the spring is always in compression, so the spring force will be in the downward direction always. Okay, whether sleeve move upward and the downward doesn't matter. Spring force will work in the downward direction always because the spring is in compression. Okay, and this is your point A, this is your arm length A, and this is arm length B. Okay, now I'm going to show you the upper position of the sleeve. That means when the sleeve moves in the upward direction, so the upper position would be like that. Here I'm going to show you. Okay, so this is your upper position. When the sleeve moves upward directions, the position would be like that. Okay, again there will be mg plus fs. Now this time mg plus fs2, because spring force will change. Okay, because sleeve is moving in the upward direction, that means the sleeve position changes, so the magnitude or the value of the friction force would be changed, but the direction would remain same. Okay, because the spring is in compression. Initially it was here. Okay, it was here, but now it was here. Okay, initially it was here, but now this time the spring force, or the, you can say that the mg plus fs 2 by 2 here, it is working here. So what is the changes? This angle must be changed. Okay, and this angle is considered as theta. Since both the arms are attached to each other, rigidly attached to each other, there will not be any relative motion between these two link, these two horizontal or the vertical link. There is no relative motion between them. So if this angle is theta, so this angle would also be theta. That means initially it was this at this position. Okay, so this angle is also theta. Okay, so this angle is also theta. This angle is also theta. Okay, that means when the sleeve arm moves theta angle, vertical arm will also move theta angle. Okay, because both are rigidly attached, there is no relative motion between both the arms. Okay, so we all know that this is the, let us consider that this is the sleeve axis. Okay, so if this is R1 initially, since this is R1 or not, this is the radius of rotation R1. Okay, and now the second time the radius of rotation becomes R2, so this becomes R2 minus R1. Okay, this becomes R2 minus R1, and we all know this is nothing but the sleeve movement. This is nothing but the sleeve movement. Yes or no? This is your sleeve movement. Sleeve moves from here to here, so this is your sleeve movement. Okay, let us consider that this is B and this is B dash. Okay, this is A, this is B, this is A, this is B. Now the new position of the sleeve is at B dash, so the sleeve movement becomes BB dash. Okay, are you getting my point? Is there any problem here? And what is the forces, remaining forces? There is the mg, this is the small m, mass of the ball, and since the ball is rotating, there will be centrifugal forces mr1 omega 1 square. Okay, similarly there will be a mg in the downward direction, and there will be a mr2 omega 2 square. Okay, I think there is no problem here. Now we will balance the equations. That means how many forces are there we have to see, and we have to balance them. Okay, so we can see here that there are mg forces. That means if I'm taking the moment about point A and neglect the obliquity, obliquity means we know that this vertical angle is having an inclination. Okay, but we will neglect it in order to find out the moment of mr omega square, like that. Okay, otherwise we will not be able to find out the moment of mr omega square about point A, unless and until we neglect obliquity. Okay, so we have to neglect obliquity in order to find out the moment about point A. Okay, so write down the next point: rotation equilibrium of governor. Rotation equilibrium of governor. So we are going to take moment to write down the taking moment about point A, about point A. And what is the important thing? Neglect the obliquity. Neglect obliquity. So when you neglect obliquity and take moment about point A, there will be you have to assume this vertical arm, or you can say this ball arm, and you have to assume it's vertical, so that we can calculate the moment about point A, that is m r1 omega square into A. Okay, so for a moment I'm going to consider this as f1. Okay, and this as f2. Okay, we will convert later. So what is the moment? That is f1 multiply A, and if we are taking moment about point A, so it is making anti-clockwise couple, and this force is making in the clockwise direction. Okay, mg plus fs1 by 2 into B, and it is making clockwise couple. So one is in the anti-clockwise direction and other is in the clockwise direction, so both will be equal to each other. Okay, both will be equal to each other. Are you getting my point? Is there any doubt? Okay, so this is as simple as we can see. So this is equal to mg. Now remember, capital M is the mass of the sleeve and small m is the mass of the fly ball. I'm going to write here, this is the mass of fly ball, and capital M is the mass of the sleeve. It is the mass of sleeve. So this is mg plus fs1 by 2 into B. We have neglect obliquity. Okay, similarly f2 into A, that is mg plus fs2 by 2 into b. Is that clear? This is your equation number 1 and this is your equation number 2. See, there are a number of objective questions is going to be made from these topics, okay, from Hartnell Governor. So you must have to remember each and every step very carefully. Okay, don't try to learn like a formula, just to see what is going on in the diagram, then you will be able to understand, then you will be able to make any equations through the diagram. Okay, so you just have to focus how I'm going to write down the equations. Okay, don't try to learn them, just focus on the process. So if you subtract equation number 2 minus equation number 1, you will see that f2 minus f1 into a is equal to, you can write down that 2 into a upon b. You just have to rearrange this equation so that mg can be neglected, or you can say that will be striked out, fs2 minus fs1. Okay, this is your equation number 3. Okay, now what is the total sleeve moment? As I already told you that this is your sleeve moment, this is your bb dash is your sleeve moment. Okay, and this length is small b and this angle is theta. So what would be the sleeve moment bb dash? This is b into theta. Okay, so I'm going to write here the sleeve moment. Write down here sleeve moment. What would be the sleeve moment? This is nothing but b dash, and which is equal to b into theta. Can I replace the value of theta? How can I replace? See, this is your theta and this is the length a, and we can say that theta would be r2 minus r1 upon a. Yes or no? See, we can write down the bb dash is equal to b into theta. Okay, similarly we can write down the r2 minus r1 is equal to a into theta. So from here theta would be equal to r2 minus r1 upon a. Okay, let me write down here that a theta is equal to r2 minus r1, and here b theta is equal to sleeve moment. So from here you can replace the value of theta, okay, in terms of r2 minus r1 upon a. Okay, so here let me write down the sleeve moment bb dash. This is b, and which becomes r2 minus r1 upon a. So this is your important relations comes out, sleeve moment. Okay, b r2 minus r1 upon a. Objective questions generally comes from this formula sleeve moment. Find out the sleeve moment, you must have to learn the diagram. Okay, then you will be able to find out what is the sleeve moment. So if I'm talking about the additional compression, see how much sleeve is moved would be equal to the additional compression in the spring. Yes or no? The additional means what? Spring is already in compression, we all know that. But when sleeve moves from B to B dash, there will be an additional compression in the spring. So how can we find out the additional compression in spring? Additional compression in spring is nothing but the sleeve movement. Okay, because how much amount of sleeve is moved is equal to the additional compression in the spring. Okay, so BB dash is equal to, so the thing is same but the name is different. Okay, the so sleeve movement is equal to the additional compression in the spring. Okay, both are same. So you can write down the additional compression in the spring. So how can you get the additional compression in spring? Just by observing the diagram, just by understanding the figure of the Hartnell Governor. Then you will be able to understand the sleeve movement and the additional compression in the spring is same. So this is additional compression in spring, which is equal to the moment. You can write down this is x2 minus x1, sleeve movement, and which is also equal to br2 minus r1 upon a. Okay, yes or no? So when you see the spring force, Fs is equal to K into X. We all know that the spring force is it. So spring force. So we can write down that the Fs2 minus Fs1 is equal to Fs1 is equal to spring constant is same because the spring is same, x2 minus x1. So we can write down the Fs2 minus Fs1 would be equal to K into B R2 minus R1 upon A. Yes or no? We can write down. And we all know that Fs2 minus Fs1 is nothing but this. So we can replace the value of this, and so from here we can get the value of spring constant K. That comes out to be 2 into F2 minus F1 upon R2 minus R1 into A upon B whole square. Okay. And if examiners ask you find out the initial compression means x1, which is equal to Fs1 upon F. Okay. Final compression, because once you get the value of spring stiffness, you will be able to find out the initial and the final compression. A, or you can write down as the thing is same. Final compression, x2 is equal to Fs2 upon K. Okay. So this is your Hartnell Governor concept. I hope you will be able to understand what is happening here, because numerical question is generally asked in the Hartnell Governor. So once you know the procedure for finding out the values, you will be able to solve the questions whether it is objective type or conventional type. Okay, doesn't matter. You can practice questions, you'll be able to solve the questions on the Hartnell Governor now. Okay, thank you.